Hello there, and welcome to The Sleepy Scientist. I'm glad you've joined me tonight, or today, depending on where you are in the world. Before we drift into the glowing heart of our favourite neighbourhood star, I'd love to know, where are you listening from, and what time is it where you are? Are you tucked into bed, ready to unwind, wrapped in a blanket on the couch? Or maybe just letting this play quiet while your cat carries out a secret mission in the shadows? If you're enjoying these gentle voyages through the cosmos and the curious corners of science, a soft tap on the like button and a kind subscription truly means a lot. It helps keep this sleepy little channel shining bright. Now, tonight's story is about a star that never sleeps. Quite the opposite of this channel, really. While the Sleepy Scientist is here to help you wind down and switch off, the sun is always on, always burning, always fusing tiny particles into the warmth and light we take for granted. A restless fire in the sky, quietly working overtime so that you can snooze in peace. We'll explore nuclear fusion, the slow, astonishing process that powers the sun. We'll glide through the solar core, follow the long, winding journey of a photon, and marvel at the delicate dance of pressure, gravity, and light. There's no rush. Let the words settle softly like stardust on your thoughts. Now, I do hope this video helps you relax and fall gently asleep, but if it ends up being too interesting and you lie awake contemplating hydrogen nuclei and ghostly neutrinos, well, there are worse things to think about at 2 in the morning. At the very least, you'll be a little wiser come sunrise. So get cozy, let your breathing slow, and let's begin. And just so we're clear, nothing in this video is intended as medical advice. I am not a doctor. I'm just a sleepy scientist who happens to be fascinated by stars that never take a nap. Once upon a time, about 4.5 billion years ago, a cloud of dust and gas drifted through the quiet darkness of space. There was nothing especially glamorous about it. It was mostly hydrogen, with a touch of helium and a smattering of heavier elements, all floating together in a sort of cosmic laziness. But as we've learned from many a slow beginning, stillness does not mean nothing is happening. Sometimes it means something is about to begin. This cloud was part of a much larger molecular nebula, a vast and frigid soup of star-making ingredients. And as with most stories in the cosmos, the tale begins with gravity. Gravity is the silent matchmaker of the universe. It pulls things together, whispers for particles to huddle close, and if you give it enough time, which space has in abundance, it builds stars. Some event, perhaps the shock wave from a nearby supernova, nudged this gentle cloud into motion. Suddenly, parts of the cloud began to collapse inward, slowly at first, then faster, swirling as they fell. What had once been a loose, lazy collection of particles began to tighten, spin, and heat up. This was no longer just a drifting patch of space fluff. This was a protostar in the making. As the gas and dust collapsed under their own gravity, the centre of the cloud grew denser and hotter. Imagine stuffing more and more people into a crowded room and turning up the thermostat. Eventually, things start to feel a little uncomfortable. At the heart of this growing mass, pressure built, temperatures soared, and somewhere around 15 million degrees Celsius, give or take, a transformation began. That was the moment the sun ignited, not with a bang or a burst, but with the quiet, astonishing onset of nuclear fusion. You see, stars aren't fireballs. That's a common misconception, and a perfectly reasonable one. After all, they're hot, they glow, and they seem to burn. But what's happening in the heart of a star is far more exotic than fire. Fire is just a chemical reaction, atoms shuffling electrons around and releasing energy in the process. But fusion is alchemy at the atomic level. It's when the very nuclei of atoms are pressed together so tightly that they merge, transforming into something new and releasing staggering amounts of energy in the process. In the case of our sun, it all starts with hydrogen. Hydrogen is the lightest and most abundant element in the universe. Each hydrogen atom is made of one proton and one electron. But in the sun's core, where the heat and pressure are unspeakably intense, those electrons are stripped away. What's left is a churning sea of naked protons and other ionized particles, jostling and colliding with incredible force. Under normal conditions, two positively charged protons don't like each other very much. They repel, the way two magnets with the same pole push apart. But in the Sun's core, the pressure is so high and the protons are moving so fast that occasionally, just occasionally, they get close enough for the strong nuclear force to take over. This force, which acts only at extremely short distances, overpowers the repulsion and snaps the protons together. When that happens, fusion begins. The specific reaction that fuels our Sun is called the proton-proton chain. It's a multi-step process, but in simple terms, here's what's going on. Two hydrogen nuclei, protons, slam into each other. If they're lucky, or unlucky depending on your point of view, they fuse to form a heavier particle called deuterium, which is a hydrogen atom with one proton and one neutron. In this process, one of the original protons transforms into a neutron via a strange little quirk of particle physics, releasing a positron, the antimatter cousin of the electron, and a neutrino, a nearly massless, ghostly particle that barely interacts with anything. This deuterium nucleus then meets another proton and fuses again, forming helium-3, a light version of helium with two protons and one neutron. Finally, two of these helium-3 nuclei collide, creating a full helium-4 nucleus, two protons and two neutrons, plus two leftover protons that go back into the mix like spare Lego pieces. The result of all this atomic hopscotch is energy, lots of it, not in a sudden explosion, but as a steady, relentless outpouring of light and heat. The energy released in the Sun's core radiates outward, bouncing its way through layer after layer until many thousands or even millions of years later, it reaches the surface and escapes into space. That light may take its sweet time getting out of the Sun, but once it's free, it sprints across the solar system at, quite literally, the speed of light. It takes just over 8 minutes to travel from the Sun to Earth. That means every ray of sunshine you feel on your skin is the product of a chain reaction that began eons ago, deep in the heart of a star that never sleeps. Now, let's rewind a bit because there's something important to appreciate here. Fusion isn't easy. It's not a casual event. It's the result of extreme conditions, temperatures of millions of degrees, pressures that would flatten anything we've ever built, and a chaotic ballet of particles in a plasma state. Plasma, by the way, is often called the fourth state of matter. It's what happens when a gas is so hot that its atoms break apart into a soup of nuclei and electrons. In the Sun's core, everything is plasma. It's not solid, it's not liquid, and it's not quite gas. It's something else entirely, like a crowd at a concert, but every person is electrically charged and moving at the speed of insanity. Because the Sun is massive, about 330,000 times the mass of Earth, it has enough gravity to sustain these fusion conditions for billions of years. It's a perfectly balanced cosmic engine. Gravity pulls everything inward, trying to collapse the star, while the outward pressure from the fusion reactions pushes back, creating a stable equilibrium. As long as fusion continues, the Sun remains more or less steady, no bigger, no smaller, just glowing contentedly in the sky like a lava lamp on an infinite timer. This period of a star's life is called the main sequence. It's the longest and most stable phase, and our Sun is smack in the middle of it. It has been fusing hydrogen for about 4.5 billion years, and it will likely continue for about 4 or 5 billion more. That's good news for us, because it means we've got plenty of sunshine left. But it's also worth noting how delicate this process really is. If the Sun were much smaller, it wouldn't have enough gravity to ignite fusion at all. It would just be a big, cold ball of gas, perhaps a brown dwarf. And if it were much larger, fusion would proceed so rapidly that the star would burn out in a few million years, a cosmic blink. In that sense, our Sun is the Goldilocks of stars, not too big, not too small, just right. And because of that, We get to bask in its gentle glow, grow our crops, power our weather, and gaze up at a sky that's been lit by the same celestial hearth for all of human history. The story of the sun's birth is really the story of cosmic chance. A random cloud, a tug of gravity, a spark of ignition, and a fusion reaction that has been humming steadily ever since. It's a tale older than life itself, yet still unfolding every second, above us and within us. Because here's the beautiful part. Every atom of carbon in your body, every bit of oxygen you breathe, every molecule of calcium in your bones, these were all forged in stars. Maybe not this star, but stars like it. Fusion doesn't just make light, it makes us. And that, perhaps, is the most quietly astonishing fact of all. The sun, forever busy, never sleeping, is not just a beacon in our sky. It's part of our origin story. We are, quite literally, the light of ancient stars cooled and walking around. Nuclear fusion. It sounds like something ripped from a science fiction novel. A futuristic power source, perhaps, or the cause of some galactic mishap in a spaceship engine room. But in truth, nuclear fusion is not science fiction at all. It is science fact, and it's been quietly lighting up our skies for billions of years. It is the process that makes stars shine, including the one we orbit so fondly and depend upon so completely, the sun. Let's start gently, peeling back the layers without any rush. Fusion, in its simplest form, is the joining together of atomic nuclei. That's it. Not splitting them apart. That's fission, the thing we do in nuclear power plants on Earth. But fusing them together, like cosmic glue bonding the tiniest bits of matter into something new. And in the process, something almost magical happens. A little bit of mass goes missing and is transformed into energy. Now this isn't just poetic, it's Einstein. Specifically, it's Einstein's famous equation E equals mc squared. Don't worry, you don't need to memorize it, but the gist is this. When a bit of mass disappears during fusion, it doesn't just vanish. Instead, it becomes energy. Lots and lots of energy. The c in the equation stands for the speed of light, which is an enormous number. And when you square that number, even the tiniest bit of missing mass gets turned into a tremendous amount of energy. The sun does this constantly. Every second, it converts about 4 million tons of matter into energy through fusion. Every single second. And that energy radiates outward, giving us the daylight we walk under and the warmth we feel on our skin. But let's step back a moment and look at what's actually fusing. Inside the sun, the star's core is composed mostly of hydrogen, the simplest element in the universe. A hydrogen atom, when you strip it down to its bare essentials, is just one proton. That's it. One tiny, positively charged particle. When you gather trillions upon trillions of hydrogen atoms in one place, like say, the core of a star, and heat them to incredible temperatures, something strange begins to happen. The electrons get stripped away, and the atoms become what's known as plasma, a roiling sea of free-floating protons and electrons. These protons zip around chaotically, crashing into each other constantly. Under normal conditions, protons repel one another. They're all positively charged, and just like trying to push the same poles of two magnets together, they resist. But inside the sun, conditions are anything but normal. Temperatures at the core soar to around 15 million degrees Celsius. That's 15 million. At those temperatures, the protons are moving so fast that they can sometimes smash together with enough force to overcome their natural repulsion. This is where the magic begins. The process that powers the sun is called the proton-proton chain. It is the dominant fusion reaction in stars the size of our sun or smaller. And though the name might sound like a breakfast cereal for physicists, it is in fact the reason you can read a book by daylight or grow a tomato in your garden. So what actually happens in this chain? First, two protons collide with enough force that one of them transforms into a neutron. This change is made possible by a quantum process called the weak nuclear force. It's called weak, but that's really just in comparison to other forces in physics. It's still powerful enough to rewrite the identity of a subatomic particle. The proton becomes a neutron, and in the process it emits a positron and a neutrino. A positron is the antimatter counterpart of an electron, like a cheerful mirror twin, and a neutrino is a nearly massless particle that zips off into the universe, barely interacting with anything. We'll talk more about those later. What you're left with now is a particle called deuterium. It's a special kind of hydrogen that contains one proton and one neutron in its nucleus. That deuterium nucleus quickly finds another proton and fuses with it, forming helium-3, 2 protons and 1 neutron. This fusion also releases a gamma ray, a high-energy photon that will spend a very long time bouncing around inside the Sun before it ever reaches us. The final step in this main chain reaction involves 2 helium-3 nuclei. When they collide, they fuse to form a helium-4 nucleus, 2 protons and 2 neutrons, and they toss out 2 extra protons like forgotten packing material. Those spare protons go back into the pool, ready to start the whole dance over again. Now, that may sound like a lot of steps, and it is, but this process happens constantly, all over the core of the Sun, every moment of every day. The Sun fuses about 620 million tons of hydrogen into helium each second. In doing so, about 4 million tons of mass are converted into energy, every second. It's almost hard to comprehend. Imagine 4 million elephants disappearing into light every second, and you're still not quite close. The energy released by this fusion is what powers the Sun's immense brightness. But oddly enough, it's not an immediate journey. The photons produced during fusion don't zip straight out to the surface and head toward Earth. Instead, they spend an incredibly long time making their way outward. The Sun's interior is so dense that these photons bounce around like frantic ping-pong balls, constantly absorbed and re-emitted by particles in the solar plasma. It can take thousands, even up to millions of years for a single photon to escape the Sun's core and reach the surface. By the time it finally breaks free and races off into space, it may be older than human civilization. Let's also pause and appreciate the temperatures and pressures involved here. The Sun's core is under a crushing weight, about 340 billion times the atmospheric pressure at sea level. If you could somehow stand in the centre of the Sun, which to be clear you absolutely could not, you'd be flattened beyond recognition in less than a heartbeat. The conditions are so extreme that matter behaves in ways that defy our everyday understanding. Particles exist in a quantum haze, simultaneously behaving like waves and dots, flickering into and out of potential states. And yet, from all this chaos and violence, the result is something remarkably constant. The Sun's output barely changes over time. It rises and sets, again and again, with near-perfect regularity. The light it emits is stable, reliable, and predictable. It is the quintessential example of chaotic beginnings yielding to orderly results. Fusion is the quiet workhorse of the cosmos, steady, slow, and unimaginably powerful. It's also worth noting that fusion is incredibly efficient. When hydrogen fuses into helium, about 0.7% of the mass is turned into energy. That might not sound like much, but consider this. Burning coal or gasoline only converts a tiny fraction of a percent of its mass into usable energy. Fusion is orders of magnitude more effective and cleaner. No smoke, no ash, no toxic byproducts. Just light, heat, and a few neutrinos for good measure. And unlike the fission reactions we use in nuclear power plants, where large atoms are split apart, releasing energy, fusion brings smaller nuclei together. The result is not only more energy per reaction, but also far less radioactive waste. Fusion, if we can ever manage to control it on Earth, would be the ultimate energy source, sustainable, safe, and practically limitless. But while we struggle to recreate fusion in our laboratories, the Sun performs it effortlessly, continuously, and with quiet grace. It does not need enormous magnetic fields or high-tech confinement chambers. It simply exists, with enough mass and pressure to let gravity and physics do the work. It is the ultimate role model for renewable energy. Still, it is humbling to remember that even the sun has limits. It has been fusing hydrogen for billions of years, and it will continue to do so for billions more. But eventually, it will run out of hydrogen in its core. When that happens, it will begin fusing helium, and then, briefly, heavier elements. But that chapter of the sun's story lies far in the future. For now, it is enough to marvel at the quiet miracle happening above us. Nuclear fusion, so easy to overlook, so easy to misunderstand, is one of the most fundamental engines of the universe. It lights the stars, shapes the galaxies, and makes life possible on a small blue planet that circles a star which, despite its fiery nature, is actually quite gentle. It is one of the great ironies of nature that something so extreme, so violent at the atomic level, results in the soft golden light of a sunset, or the warmth on your face on a spring morning. Fusion is a furnace, yes, but it is also a gift, an ancient glowing reminder that even the smallest particles, under the right conditions, can come together to create something astonishing, something bright, something that never sleeps. Let us imagine just for a moment that we could dive deep beneath the glowing surface of the sun. Not with a spaceship or a heat-proof submarine, those would melt before getting even remotely close. But with our minds, safe and curious, gently floating downward through the golden layers of this immense and radiant star. As we descend, we leave behind the familiar glow of sunlight and begin to enter a world of staggering pressure, crushing density and temperatures that defy earthly imagination. We are venturing into the solar interior, the sun's secret heart, the realm where nuclear fusion quietly does its work. At the very centre of the sun lies the core, a place so extreme that it challenges even the most robust analogies. The pressure here is around 250 billion times greater than the atmospheric pressure on Earth at sea level. Just to give that some gentle perspective, if you placed a single postage stamp in the core of the sun, the force pressing down on it would be the equivalent of millions of tons. Not exactly the kind of environment where you'd go for a stroll. The temperature in this stellar pressure cooker reaches about 15 million degrees Celsius. At that heat, nothing remains as it is. Atoms lose their electrons, forming an energetic, electrified soup known as plasma. Plasma is the fourth state of matter, and it's both simple and strange. Think of it as gas that's been supercharged. The particles have so much energy that they no longer hold on to their electrons, and everything becomes a seething sea of charged particles. It's the sun's native language, the state in which nearly all of its matter exists. But what truly defines the core is not just its heat or its pressure, but its role. This is the site of nuclear fusion, the very reaction we explored in detail earlier. Every second, countless hydrogen nuclei crash into one another, some with just enough energy to overcome their mutual repulsion and fuse into helium. This fusion releases energy in the form of gamma rays, neutrinos and kinetic motion. It is, quite literally, where sunlight begins. Interestingly, although the sun is unimaginably hot, it is not hot enough, at least by fusion standards. In order for fusion to occur, the hydrogen nuclei must get close enough for the strong nuclear force to bind them together. But because they are both positively charged, they repel one another with significant force. At the temperatures found in the sun's core, their average energy isn't quite sufficient to overcome this repulsion. So why does fusion happen at all? The answer lies in quantum mechanics, specifically a phenomenon called quantum tunneling. It's a bizarre and wonderful concept that defies everyday experience. In classical physics, if a ball rolls toward a hill that's too steep, it simply rolls back down, end of story. But in the quantum world, particles aren't like tiny billiard balls. They are described as probability waves, and there's always a small chance they can tunnel through an energy barrier they technically shouldn't be able to overcome. It's as if the ball, instead of bouncing back, simply vanishes and reappears on the other side of the hill. No digging, no drilling, just an elegant little hop through space. In the core of the Sun, quantum tunneling allows hydrogen nuclei to fuse even when they don't have quite enough energy to overcome their mutual repulsion on their own. It's a rare event, probabilistically speaking, but the Sun is so large and full of hydrogen that even rare events happen constantly. It's like rolling a die with a million sides and needing to land on just one specific number. If you roll that die trillions of times every second, you're still going to see that special number show up quite often. Once a fusion reaction occurs and energy is released, that energy doesn't immediately shoot outward like a flashlight beam. Instead, it begins a long and arduous journey through the Sun's interior. This process is not straightforward. It's not even vaguely efficient. The gamma rays created during fusion ricochet off particles in the surrounding plasma, being absorbed, re-emitted, scattered, and bounced in every direction imaginable. It's as though each photon is playing the most confusing game of pinball ever devised. This inner region surrounding the core is known as the radiative zone, and it acts like an immense fog of particles. Light produced here can take an astonishingly long time to escape, anywhere from 10,000 to over 1,000,000 years, depending on the particular path a photon takes. So the sunlight we feel on our skin today began its journey when mammoths roamed the earth, when glaciers carved out valleys, when human ancestors huddled around fires. It is ancient energy, just arriving. Eventually, after bouncing its way outward for a geological eternity, this energy reaches the next layer of the Sun, the convective zone. Here, the density of the Sun has dropped enough that radiation alone can no longer carry energy efficiently. Instead, the Sun relies on convection, a process we're all more familiar with. If you've ever watched a pot of soup boiling on the stove, you've seen convection in action. Hot material rises, cool material sinks, and the whole system churns in an endless loop. In the Sun's convective zone, giant bubbles of hot plasma rise toward the surface, cool slightly, and sink back down again. This movement stirs the outer layers of the Sun like a slow solar stew. Each convective cell can be hundreds of thousands of kilometers across. These massive, slow-moving rivers of plasma circulate energy from the deep interior to the outer layers of the Sun. They also give rise to much of the Sun's visible activity, sunspots, flares, and the solar magnetic field, but we'll gently save those wonders for another time. As we continue our mental descent, let's take a quiet moment to appreciate the scale of the Sun's interior. From the centre to the surface, the Sun spans nearly 700,000 kilometres. That's over 100 times the diameter of the Earth. Yet, the core itself, the region where fusion actually occurs, is relatively small in comparison. It extends to only about 1/4 of the Sun's total radius, or roughly 175,000 kilometres. That's still enormous by our standards, roughly 14 Earths lined up side by side, but in the vastness of the Sun, it's just the innermost chamber of a much larger, more intricate structure. The radiative zone, where energy meanders outward through photon pinball, extends from the edge of the core out to about 70% of the Sun's radius. Beyond that lies the convective zone, which takes up the final 30%. So while fusion only happens in the deep centre, the effects ripple outward through every layer, shaping the Sun's behaviour and ultimately determining how its energy reaches us. One particularly fascinating thing about the Sun's interior is that we can't observe it directly. There are no windows into the core, no telescopes that can see fusion in action. Yet, remarkably, we've learned an enormous amount about this hidden world. Scientists use a combination of theoretical models, computer simulations, and observational data to peer beneath the Sun's surface. One of the most powerful tools for doing this is helioseismology, a field that studies sound waves travelling through the Sun. Just as geologists study earthquakes to learn about Earth's interior, solar physicists observe ripples and oscillations on the Sun's surface to infer what's happening deep inside. These waves are caused by turbulent motions in the convective zone, and they carry subtle information about the density, temperature, and composition of the layers they pass through. Another important source of information comes from solar neutrinos. These ghostly particles are created during fusion reactions and pass through the sun, and everything else almost entirely unimpeded. They zip through planets, people, and even lead shielding as though those obstacles weren't there. By detecting solar neutrinos here on Earth, scientists can confirm that fusion is happening in the core, and even estimate the rate at which it occurs. Our understanding of the sun's interior is constantly evolving, but one thing is certain: it is a dynamic, complex, and utterly alien environment. There is no solid surface, no clear boundary lines, just layer upon layer of plasma, pressure, and heat, each with its own role to play in the delicate symphony of starlight. And yet, despite all this complexity, the sun remains wonderfully stable. It has been fusing hydrogen and shining steadily for billions of years, and it will continue to do so for billions more. This slow and steady process is not just the engine of the sun, it is the quiet heart of life on Earth. Every tree, every flower, every breath we take owes something to the energy generated in that distant core. So the next time you feel the sun on your face, pause for a moment. Behind that warmth is a chain of extraordinary events: particles colliding in a sea of plasma, quantum tunneling across barriers, and ancient photons emerging from a million-year journey through fire and gravity. The sun is not just a bright light in the sky, it is a cathedral of physics, a slow, burning miracle that never sleeps, and at its heart lies a furnace, not of fire, but of fusion, calm, relentless, and beautiful. If the sun had a recipe, it would be surprisingly simple. Take 4 hydrogen nuclei, protons technically, mix them together under unimaginable pressure and heat, sprinkle in a bit of quantum mechanics, and wait. The result? A helium nucleus and enough energy to keep our planet warm, our plants photosynthesizing, and our cats napping in sunbeams. This deceptively simple process is called the proton-proton chain, and it is the sun's signature dish, the nuclear reaction that fuels our star's radiance, particle by particle, second by second. The proton-proton chain might sound like something you'd find in a chemistry set for extremely advanced toddlers, but it is in fact the main engine behind the sun's light and heat. It is how hydrogen, the lightest and most common element in the universe, transforms into helium, releasing energy in the process. This reaction is incredibly efficient on the scale of the universe, but also incredibly slow, and that's a good thing. A very fast-burning sun would be bright and beautiful for about 10 million years. Then it would run out of fuel and disappear in a puff of stellar exhaustion. Fortunately for us, the proton-proton chain is a very patient process. Let's take it step by step, one gentle nuclear collision at a time. We begin with 2 protons. These are the bare nuclei of hydrogen atoms, stripped of their electrons in the sun's roiling plasma. They're positively charged and naturally repel one another, like 2 people awkwardly trying to get through the same narrow doorway at the same time. But in the sun's core, the conditions are anything but normal. Temperatures reach around 15 million degrees Celsius, and the density is so high that these protons are constantly bumping into each other. Occasionally, very occasionally, 2 protons get close enough that quantum tunneling kicks in. They slip past the repulsion barrier and get close enough for the strong nuclear force to do its work. When that happens, something quite odd occurs. One of the protons transforms into a neutron. This is a rare and remarkable event. It involves the weak nuclear force, one of the 4 fundamental forces of nature. In this moment, a proton emits a positron, the antimatter version of an electron, and a neutrino, a ghostly, nearly massless particle, and becomes a neutron. The result is a deuterium nucleus, which is simply a proton and a neutron bound together. This is the first and slowest step of the proton-proton chain. It is astonishingly rare for any given proton to undergo this reaction. A single proton in the Sun can expect to wait about 10 billion years before it successfully participates in this first fusion event. Fortunately, the Sun contains an absurd number of protons, something like 10 to the power of 57. So even though the chances for each individual are low, the overall number of successful reactions is more than enough to keep the Sun humming along. Next, the newly formed deuterium nucleus doesn't wait around. It's quickly scooped up by another passing proton, and the two fuse to form a helium-3 nucleus. This helium-3 has 2 protons and 1 neutron. In the process, a gamma-ray photon is emitted. These high-energy photons are the very beginning of what we eventually perceive as sunlight, though their journey to the surface, as we've already explored, is anything but direct. Now we've got helium-3, a halfway point in the proton-proton chain. From here the reaction can follow one of several branches, but in the Sun, the most common path is known as the pp-I chain. In this version, 2 helium-3 nuclei collide, fusing to form one helium-4 nucleus, 2 protons and 2 neutrons, and ejecting 2 leftover protons. These free protons go back into the proton soup, ready to begin the whole process all over again. And that's it. From 4 hydrogen nuclei, we get 1 helium nucleus, 2 spare protons, and a tremendous amount of energy. The mass of the resulting helium nucleus is ever so slightly less than the total mass of the 4 original protons. The difference, thanks to Einstein's famous equation, becomes energy. The Sun loses about 4 million tons of mass every second this way, converting it into energy in the form of photons, neutrinos, and the kinetic motion of particles. Let's take a moment to appreciate that. 4 million tons every second. That's roughly the mass of 20,000 aircraft carriers disappearing every second, transformed into pure energy. And the Sun has been doing this for over 4.5 billion years. Despite all this, it's still got enough hydrogen left to continue this fusion dance for billions more. Stars, it turns out, are excellent long-term planners. Now you might be wondering, if this process is so powerful, why doesn't the Sun explode? The answer is balance. Gravity pulls inward, trying to collapse the star under its own immense weight. But the energy released by fusion creates an outward pressure. These two forces are locked in a celestial tug-of-war, perfectly balanced, creating a stable, glowing orb in the sky. This state is known as hydrostatic equilibrium, and it's the reason the Sun hasn't turned into either a black hole or a puff of gas. The proton-proton chain isn't the only way stars fuse hydrogen, by the way. In larger stars, those with higher core temperatures, the carbon-nitrogen-oxygen cycle, or CNO cycle, becomes more dominant. It uses heavier elements as catalysts to speed up the fusion of hydrogen into helium. But in stars like our Sun, with its relatively moderate core temperature, the proton-proton chain reigns supreme. It's also worth noting just how long this process has been going on. Long before Earth formed, long before any planets swirled into existence, the Sun had already ignited. Fusion began when the Sun was still a baby star, a protostar just finding its footing in the universe, and it will continue long after many of Earth's mountains have crumbled and its oceans have evaporated. We are living in a moment that, from the Sun's point of view, is entirely unremarkable, just another 100 million years or so in a very long and steady lifetime. But the effects of fusion ripple far beyond the Sun's core. The energy released in the proton-proton chain fuels the entire solar system. It drives the winds on Earth, powers the weather, fuels the growth of plants through photosynthesis, and ultimately provides the energy we get from food, fossil fuels, and even our own bodies. Every bite of bread, every breath of air, every flickering campfire traces its energy lineage back to the heart of the Sun. And those neutrinos, those ghostly particles created in the very first step of the proton-proton chain, they're passing through you right now. Billions of them. Every second, streaming out of the Sun and through the Earth without so much as a ripple. They barely interact with matter, which makes them incredibly difficult to detect, but also incredibly useful as direct messengers from the core of the Sun. By studying neutrinos, scientists can confirm that fusion is indeed happening right now, deep within our star. For many years, there was a mystery known as the solar neutrino problem. Early detectors on Earth only observed about 1/3 of the expected number of neutrinos from the Sun. This was deeply puzzling. Did we misunderstand fusion? Was something wrong with our models of the Sun? Eventually, the answer came from a surprising source: particle physics. It turns out that neutrinos come in 3 types, or flavors, and they can change from one type to another as they travel. The early detectors could only see one flavor, hence the shortfall. Once this was understood, the missing neutrinos were accounted for, and physicists everywhere breathed a collective sigh of relief. So there you have it, the proton-proton chain. It is in a sense the quiet heartbeat of the Sun. It doesn't roar or rage, it hums, it pulses, it gently transforms the most basic building block of the universe into something new. And in doing so, it lights up the sky and supports life on a tiny blue dot, orbiting 93 million miles away. It's a lovely irony that the most powerful source of energy in our lives is also one of the slowest and most delicate. Fusion in the Sun is not about explosions or instant gratification. It's about steady patience, quiet endurance, and the remarkable consequences of small things coming together under the right conditions. The next time you see the sunlight casting long shadows at dusk, or feel the warmth of morning on your skin, remember this. Every ray of light, every flicker of warmth, began with 4 little protons in the heart of a star. They danced, they fused, they changed the universe just a little, and that change rippled outward, across space, across time, until it found you. The Sun may appear as a single glowing sphere from our earthly perspective, a golden coin in the sky, rising and setting with steady grace. But beneath that serene surface lies a rich, layered complexity. The Sun is not one uniform ball of fire, nor a simple orb of glowing gas. It is a marvel of structure, carefully divided into zones, each with its own role in the journey of energy from the core to the cosmos. Understanding these layers is a bit like understanding the layers of the Earth, or even the layers of a cake, if the cake were made of plasma and had a core temperature of 15 million degrees Celsius. Let's take a leisurely stroll through the structure of the Sun, starting at the core and working our way out to the shimmering edge. From the inside out, the Sun is composed of the core, the radiative zone, the convective zone, the photosphere, the chromosphere, and the corona. Each of these regions plays its part in the grand symphony of solar life. They are not separated by neat boundaries, but rather blend into one another, shifting subtly in temperature, density, and behaviour. We've already spent time in the core, that furnace where hydrogen fuses into helium and energy is born. It occupies about the innermost 25% of the Sun's radius, and produces virtually all of the Sun's energy. Even though the core makes up only a small fraction of the Sun's volume, it contains almost half of its total mass. That's a lot of weight packed into a tight seething ball of plasma. Surrounding the core is the radiative zone, which stretches from roughly 25% to 70% of the way toward the Sun's surface. In this region, energy travels primarily in the form of photons, tiny packets of light. But they don't move in straight lines. Oh no, nothing so simple. Instead, these photons are absorbed and re-emitted by the surrounding particles in a kind of cosmic pinball machine. A single photon created in the core may take thousands to even millions of years to zigzag its way through the radiative zone. It's a slow, painstaking journey, and no 2 photons follow the same path. This is because the plasma in the radiative zone is extremely dense. So dense, in fact, that light cannot travel far without interacting with a particle. Every time a photon encounters an electron or an ion, it is absorbed and then re-emitted in a random direction. This process, called radiative diffusion, is what gives the zone its name. It's like walking blindfolded through a crowded party, bumping into someone every 2 steps and changing direction each time. If you were a photon, you'd be very, very dizzy. Eventually energy reaches the outer edge of the radiative zone and enters the convective zone, where the physics changes dramatically. The plasma here is cooler and less dense, which means radiation is no longer the most efficient way to transport energy. Instead, the sun switches to convection, the same process you see in boiling water or a pot of soup. Hot material from deeper inside the sun rises toward the surface, cools down slightly, and then sinks back down to be reheated. This cycle repeats endlessly, forming massive churning currents of plasma. These convective motions are not subtle, they are enormous. Some convective cells can be the size of entire continents. The tops of these cells can be seen on the sun's surface as granules, tiny grainy patterns that give the sun a slightly mottled appearance when viewed up close. Each granule is a window into a convective cell, a place where hot plasma is rising in the center and sinking at the edges. A typical granule might be 1,000 kilometers across and last for about 10 minutes before dissolving into the ever-changing solar surface. Above the convective zone lies the photosphere. This is the part of the sun that we see with our eyes. It's what we think of as the surface of the sun, even though it's not solid. The photosphere is actually a thin layer, only a few hundred kilometers thick, where the sun becomes transparent to visible light. In other words, it's where the photons, after bouncing their way out of the radiative zone and rising through the convective flows, finally escape into space. The temperature here is about 5,500 degrees Celsius, which is cool compared to the core, but still hot enough to make metal vaporize and atoms dance. The photosphere is where sunspots appear, those dark, cooler regions where intense magnetic fields suppress convection and slightly reduce the surface temperature. Though they look small from Earth, sunspots can be larger than our entire planet. Just above the photosphere is the chromosphere, a layer that glows faintly with a reddish hue, visible only during solar eclipses or with special instruments. It is a bit of an oddball in the sun's structure. Unlike the layers beneath it, where the temperature gradually decreases with altitude, the chromosphere gets hotter the farther you go from the surface. This reversal is one of the sun's many little mysteries. The temperature in the chromosphere can rise to about 20,000 degrees Celsius, heated by a combination of shock waves and magnetic activity. Above the chromosphere is the corona, the sun's outer atmosphere, and here things get truly strange. The corona extends millions of kilometers into space and is so hot, reaching temperatures of over 1 million degrees Celsius, that it completely defies our expectations. How can the outermost layer of the sun be hotter than the layers below it? Shouldn't it be cooler as you move away from the core? This conundrum has puzzled scientists for decades and is still not fully understood. One leading theory involves magnetic reconnection, an energetic process where twisted magnetic field lines snap and rejoin, releasing bursts of energy. Another involves waves called alpha waves, rippling through the plasma and heating it from within. The truth may be a combination of factors, and researchers continue to study the corona using satellites like the Parker Solar Probe and ground-based observatories. Despite its high temperature, the corona is incredibly sparse, far less dense than the sun's interior. This low density means that, while the temperature is high, the total amount of energy in the corona is relatively low. It's hot, but it wouldn't feel hot to you. In fact, if you could somehow float in the corona, you'd freeze rather quickly. Temperature, after all, is not just about how fast particles are moving, it's also about how many of them there are, and in the corona there just aren't very many. The corona is also the source of the solar wind, a stream of charged particles that flows outward from the sun in all directions. These particles travel through the solar system at speeds of up to 800 kilometers per second, brushing past planets, shaping magnetic fields, and even creating the auroras on Earth. When the solar wind interacts with Earth's magnetic field, it can also disrupt satellites, power grids, and communication systems. So the next time your GPS is a bit off or your internet hiccups, you might just have the sun to thank. Let's take a moment to appreciate how far we've come in our mental journey through the sun. From the heart of fusion deep in the core, to the chaotic photon shuffle in the radiative zone, to the boiling plasma of the convective layer, and finally to the layers we see and feel, the photosphere, chromosphere, and corona. Each layer is a step in the transformation of energy, a part of the sun's long and complex process of turning matter into light. What's especially beautiful about the sun's structure is how it reveals the balance between simplicity and complexity in nature. At its core, the sun is powered by a single reaction, hydrogen into helium, and yet the consequences of that reaction ripple outward through a web of processes, each more fascinating than the last. Gravity, pressure, heat, light, and magnetism all come together to create a system that is both elegant and wild. Even though the sun is nearly 150 million kilometers away, its layered structure affects us directly. The heat we feel, the light we see, the patterns of weather, the behavior of our technology, all are influenced by this distant, ever-burning star. The sun's layers are not just zones of plasma, they are pages in the story of a life on Earth. And perhaps that's the most humbling thought of all, that here we are on a small spinning world, warmed by a star we cannot touch but depend on completely. A star made of layers within layers, processes within processes, all working together with cosmic patience and consistency. So the next time you look up at the sun, filtered through the leaves or reflected in a puddle, remember, what you're seeing is just the very top layer of an astonishing journey, one that began deep in the core long ago with a quiet fusion of hydrogen atoms. From that single reaction flows the light that paints your world. Light, as we experience it, seems so immediate. You flick a switch, and there it is. The sun crests the horizon, and your world floods with warmth and gold. It feels almost instantaneous. But when we talk about light from the sun, the story is anything but instant. In fact, every sunbeam you've ever basked in began its journey eons ago, in the searing heart of the sun, long before mammals had even evolved, long before Earth had continents in their present form, and long before you ever reached out your hand to feel the morning warmth. To understand this slow and wondrous journey, let us return once more to the core, the blazing origin of it all. Deep within this sphere of fusion, hydrogen atoms fuse to create helium, releasing energy in the form of gamma-ray photons. These photons are the first tangible products of nuclear fusion, but their story has only just begun. They are born into a place so dense, so full of charged particles, that escape is not simply difficult, it is astronomically improbable. Imagine for a moment that you're a photon, newly formed in the sun's core. You're energetic, enthusiastic, and ready to race off into space. But there's a problem. You're not alone. You're surrounded by an unfathomable number of protons, electrons, and other photons, all jostling in a crowded, chaotic plasma. You try to zip ahead, but within a fraction of a millimeter, you're absorbed by a nearby electron. Your energy is momentarily swallowed, only to be re-emitted a moment later in a random direction. Maybe you move left, maybe right, maybe back where you came from, and the cycle begins again. This process is called radiative diffusion. It's the slow, meandering, chaotic migration of energy through the sun's radiative zone, where photons are constantly absorbed and re-emitted by particles in the plasma. You can think of it as the world's most exhausting relay race, with no clear direction and a virtually infinite number of baton handoffs. A photon's path out of the sun is more like the trail of a leaf caught in a whirlpool than a straight line across open water. On average, a photon travels only a few millimeters before interacting with another particle. Then it changes direction, over and over again. Statistically speaking, this means it takes an extraordinarily long time to reach the outer layers of the sun. Estimates vary, but the journey can take anywhere from 10,000 to over 1 million years. That is not a typo. The light you feel on your face today may have been created before the last ice age, before the pyramids, before language as we know it. And here's the twist. It's not even the same photon anymore. During its journey outward, the original high-energy gamma-ray photon loses energy through repeated interactions. Each time it's absorbed and re-emitted, it can be degraded in energy, and by the time it finally reaches the sun's surface, it's no longer a gamma-ray. It has become visible light, infrared or ultraviolet radiation, the kinds of light we're more familiar with. So while we refer to this journey as if one photon is making a single long trek, it's really more like a lineage, a series of photons, each passing the baton of energy from one interaction to the next. As the energy moves outward, it eventually reaches the base of the convective zone, where the rules change dramatically. In this region, the sun's plasma becomes cooler and less dense, and radiative transfer is no longer efficient. Instead, the sun shifts to using convection to move energy upward. It's a bit like how a pot of soup doesn't rely on tiny light packets to cook itself. It relies on boiling. Here in the convective zone, blobs of hot plasma rise toward the surface, cool as they near the top, and then sink back down again to be reheated. These plasma bubbles are enormous, often spanning hundreds of thousands of kilometers, and they churn slowly but steadily. This movement forms convection cells, massive loops of circulating plasma that transport energy far more efficiently than radiation can in this region. Once the energy reaches the top of the convective zone, it arrives at the photosphere, the layer of the sun that we see with our eyes. Here, the density of plasma becomes low enough that photons can escape into space without being immediately reabsorbed. This is the moment of freedom. After thousands or millions of years trapped in the sun's interior, the photon, or at least its energy, bursts forth, streaming into space at the speed of light. From this point on, things finally speed up. Light travels at nearly 300,000 kilometers per second, so it takes just over 8 minutes for sunlight to journey across the 93 million miles between the sun and Earth. In cosmic terms, that is the blink of an eye. After such a long and complicated voyage through the sun itself, the final leg of the journey is astonishingly swift and smooth. And then, at last, sunlight arrives. It touches the leaves of trees, the surface of oceans, the feathers of birds in flight. It powers photosynthesis, triggers chemical reactions in your skin, glints off windows, and warms the asphalt. It paints the sky in shades of dawn and dusk and makes shadows dance across the ground. It is the same energy that began its life as a gamma ray in the sun's core so very long ago, now arriving as a soft visible glow. But sunlight is not just pretty, it's also incredibly informative. By analysing the spectrum of light from the sun, scientists can determine its composition, temperature, movement, and more. Light carries within it the fingerprints of the atoms it passed through. It tells us what the sun is made of, mostly hydrogen and helium, with traces of heavier elements like carbon, oxygen, and iron. It reveals the motion of solar material, whether it's moving toward or away from us. It shows us sunspots, flares, and magnetic storms. In short, sunlight is a messenger, carrying news from the heart of a star to the surface of a planet. And this light does more than inform, it sustains. Nearly all life on Earth depends on solar energy in some form. Plants capture sunlight through photosynthesis, converting carbon dioxide and water into glucose and oxygen. Animals eat the plants, and other animals eat those animals, creating a food chain built on solar power. Even fossil fuels stored deep within the Earth are the ancient remains of plants and microorganisms that once captured sunlight millions of years ago. Light from the sun also drives our weather and climate. It heats the atmosphere unevenly, creating wind, ocean currents, and storms. It shapes the rhythms of day and night, guiding the behavior of animals, plants, and even human sleep patterns. Without the steady arrival of solar energy, Earth would be a frozen, lifeless rock drifting in darkness. But the journey of light doesn't stop at Earth. It continues outward, spreading through the solar system and beyond. Some of it reflects off the moon, creating the soft silver light of night. Some of it illuminates the planets, rings and comets of our cosmic neighbourhood. Some of it escapes into the vastness of space, travelling for billions of years, perhaps passing by other stars, other worlds, and other distant observers. And all of it began in a place we cannot see, cannot touch, a fusion reaction in the sun's core, quiet and relentless. The sun doesn't roar like a fire, it hums, it pulses, it breathes light into the solar system, one improbable photon at a time. The sheer improbability of this entire process is part of what makes it so beautiful. From fusion in the core, to the chaotic bounce of photons through the radiative zone, to the slow churn of convection, to the final sprint across the vacuum of space. It is an epic, invisible odyssey. A journey of energy across millions of years and millions of kilometers, ending in a moment of golden light on your face. It is easy to forget in our electrically lit world just how ancient and meaningful sunlight is. It is not just a convenience, it is not just a backdrop, it is the evidence of fusion, of balance, of the strange and elegant physics that holds our universe together. So the next time you watch sunlight filtering through the trees or reflecting off a still lake, take a moment to imagine where that light has been. It is not just light, it is history. It is time, made visible. It is the echo of a fusion reaction, born in darkness, emerging into brilliance, and finding its way to you. While the sun may appear at first glance to be a smooth and steady beacon in the sky, reliable, warm, and eternally bright, it is also an incredibly busy place. Beneath that glowing exterior, the sun is constantly creating particles that we never see, never feel, and almost never notice. These particles stream out of the sun in unimaginable numbers, slipping through the planets, through your body, through the Earth itself, without so much as a whisper. These are neutrinos, the most elusive ghost-like messengers in the universe, and they are born in the very heart of the sun during the very process that powers it, nuclear fusion. To appreciate just how strange and marvellous neutrinos are, let us begin where they are born, in the fusion reactions of the solar core. As we've discussed in earlier chapters, when two protons fuse in the first step of the proton-proton chain, one of them must transform into a neutron. This rare and magical transformation involves the weak nuclear force and produces three things: a neutron, a positron, and a neutrino. The positron quickly meets its match in an electron, and the two annihilate each other in a burst of gamma radiation. But the neutrino? It simply leaves. Unlike photons, which get trapped in the sun's interior for thousands or millions of years, neutrinos don't linger. They don't bounce. They don't interact. They just pass through matter as if it weren't there. Within moments of being created, they travel straight out of the sun, through its layers, and into the cosmos at nearly the speed of the light. It takes a photon perhaps 1,000,000 years to leave the sun, but a neutrino, a little over 2 seconds. And once they leave, they keep going. Neutrinos are so light, so neutral, and so unbothered by electromagnetic forces that they can travel through light years of solid lead without interacting with a single atom. They are the Houdinis of the particle world, always escaping, always slipping through the cracks, nearly impossible to catch. Yet despite this incredible shyness, the sun produces them in staggering quantities. Every second, it emits about 200 trillion neutrinos. That's a 2 followed by 38 zeros. And because these neutrinos move in all directions, a small fraction of them pass through Earth. In fact, about 65 billion solar neutrinos pass through every square centimetre of your body every second. Not per day, not per hour, every single second. Right now, as you listen to this sentence, billions of neutrinos are zipping through your skin, your bones, your bloodstream, and out the other side, as if you were made of nothing more than fog. This may sound unsettling, but rest assured, neutrinos are harmless. They almost never interact with matter. In fact, it's because they almost never interact that they're so difficult to detect. To catch even a handful of them, scientists must build enormous detectors, often located deep underground to shield them from cosmic rays and other background radiation. These neutrino detectors are engineering marvels. Quiet, dark chambers filled with vast volumes of ultra-pure water or specialized fluids, watched over by arrays of sensitive light sensors. One of the most famous of these is the Super Kamiokande detector in Japan. It's located 1 kilometer underground in a former mine and contains 50,000 tons of ultra-pure water surrounded by over 10,000 photomultiplier tubes. When a rare neutrino does interact with a water molecule, it can produce a faint flash of light known as Cherenkov radiation, a brief, bluish glow that reveals the presence of this otherwise invisible visitor. By observing these rare interactions, scientists can count neutrinos, study their properties, and confirm that fusion is happening in the Sun exactly as theory predicts. In the mid-20th century, scientists began building such detectors to look for solar neutrinos, expecting to find a steady, predictable stream, and they did find neutrinos, but only about a third as many as they had predicted. This puzzling shortfall became known as the solar neutrino problem. For decades, physicists wondered whether something was wrong with our understanding of fusion. Was the Sun cooling down? Was fusion slowing? Eventually, the mystery was solved, not by adjusting our model of the Sun, but by refining our understanding of neutrinos themselves. It turns out that neutrinos come in 3 different types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The detectors at the time were only capable of observing electron neutrinos, the type created in the Sun. But as neutrinos travel through space, they can oscillate, changing from one flavor to another like tiny subatomic shapeshifters. This discovery, called neutrino oscillation, won the Nobel Prize and revolutionized our understanding of particle physics. It also explained the missing neutrinos. The Sun was producing the correct number all along. It's just that many of them were changing flavor on their way to Earth, becoming temporarily invisible to the detectors. Once new detectors were built to recognize all 3 types of neutrinos, the numbers lined up beautifully. And so, neutrinos became not only messengers of fusion, but also messengers of new physics, proof that particles can morph in flight, that mass is not as fixed as once believed, and that the universe holds more secrets than we ever imagined. Through neutrinos, we glimpsed both the inside of the Sun and the flexible, fluid nature of the quantum world. There is something profoundly elegant about this. The Sun does not just shine, it sends out clues. Photons may take ages to reach us, but neutrinos arrive almost instantly, untouched, unfiltered, and unspoiled by their journey. They are the Sun's direct whispers, telling us what is happening in its core right now, not what happened a million years ago. They let us monitor the Sun's fusion engine in real time, offering an early warning system for any changes in its behavior. Not that we expect any sudden changes, but it's comforting to have an inside line. Beyond the Sun, neutrinos play vital roles in many astrophysical processes. They are released in colossal numbers during supernovae, helping to blow apart the dying stars and seed the cosmos with heavy elements. They may even hold clues about the early moments of the universe, carrying information from the Big Bang itself. And some physicists believe that studying neutrinos might help us answer some of the deepest questions in cosmology, such as why the universe contains more matter than antimatter. Despite their elusiveness, neutrinos are among the most abundant particles in the universe, second only to photons. And yet, because they interact so rarely, they don't form atoms or molecules. They don't build stars or planets or people. They are everywhere, but they leave no trace, like shadows without a source. Still, their importance cannot be overstated. Without neutrinos, fusion in the Sun might not proceed in the same way, and without our ability to detect them, we would know far less about what is happening inside our own star. They are silent partners in the grand experiment of existence. And perhaps there's something comforting in that even as we sit here, quietly listening, something extraordinary is happening, not just out in space, but through us. That billions of particles are gliding through the walls, the air, and our own bodies every second, carrying messages from a star 93 million miles away. That we are, in a very real sense, connected to the sun not just by heat and light, but by the soft, silent passage of neutrinos, constant, invisible reminders of the fusion that makes all life possible. So the next time you step into the sunlight, take a moment to think beyond what you can see. The warmth on your skin is from photons that travelled millions of years. But deep beneath your awareness, an endless stream of neutrinos is passing through you, each one a subtle note in the sun's ongoing song. They are the particles that never stop, the witnesses to every fusion reaction, the most faithful travellers in the cosmos, and you, whether you notice or not, are part of their journey. At the heart of every star lies a delicate balancing act, a cosmic tug-of-war between two colossal forces. On one side is gravity, that persistent, invisible hand that pulls everything inward, relentlessly trying to collapse the star into a smaller and smaller volume. On the other side is pressure, created by the furious energy produced in the star's core through nuclear fusion, pushing outward with equal determination. This quiet standoff is what keeps the sun alive and glowing, neither imploding into darkness nor bursting apart in a blaze of unrestrained energy. It is called hydrostatic equilibrium, and it is one of the most elegant and essential principles in astrophysics. Let us begin with gravity, the sculptor of stars. Gravity is the reason the sun exists in the first place. Long ago it pulled together a cloud of gas and dust, drawing each atom closer and closer, until the pressure and temperature at the centre were high enough to ignite nuclear fusion. From that moment on, gravity's role became both more urgent and more constrained. It continued to pull, to compress, to push inward, but now it was opposed by a new force, the outward pressure generated by the energy released in fusion reactions. When hydrogen nuclei fuse into helium in the sun's core, they release an enormous amount of energy in the form of photons, neutrinos, and kinetic energy. These energetic particles exert pressure on the surrounding material, pushing it outward. This pressure is not a simple blast or an explosion. It is a steady, persistent force, like steam building up in a sealed chamber. It's what keeps the outer layers of the sun from falling inward, and what maintains the sun's spherical shape over billions of years. Hydrostatic equilibrium is achieved when the inward pull of gravity is exactly balanced by the outward push of pressure at every point within the star. Not just at the surface, but in every layer, from the blazing core to the wispy corona. It is a dynamic balance, not frozen, but continuously maintained as conditions shift and evolve. If fusion were to suddenly stop, pressure would drop and gravity would win. The sun would begin to contract. If fusion somehow accelerated out of control, pressure would rise and the sun would begin to expand. But because the processes are so finely tuned, the sun remains stable. This is the cosmic version of walking a tightrope, except instead of balancing on a wire, it's balancing an entire star. What's remarkable is just how sensitive this balance is. The rate of nuclear fusion in the sun's core is governed by the temperature and density there. A small increase in core temperature can lead to a disproportionately large increase in the rate of fusion. This in turn increases the pressure and causes the core to expand slightly, which lowers the temperature and slows the fusion rate. Likewise, if the temperature drops, fusion slows, pressure decreases, and gravity causes the core to contract, heating it back up and restoring the balance. This feedback loop keeps the sun's output remarkably steady over time. It's a self-regulating system like a cosmic thermostat, always adjusting to maintain equilibrium, and it works. The sun's luminosity has increased by only about 30% over the past 4.5 billion years, a slow and steady rise that has given life on Earth the stability it needs to thrive. But what would happen if this balance were disrupted? Let's imagine, purely as a thought experiment, that fusion in the Sun's core were to stop suddenly. Perhaps because the hydrogen fuel had been exhausted, or because a fictional space wizard snapped his fingers. Without fusion, there would be no more energy pushing outward. The core would no longer resist gravity's pull, and it would begin to collapse. As the core contracted, it would heat up, because when you compress a gas, it gets hotter. This increased temperature might ignite a new round of fusion reactions involving helium or other heavier elements, depending on how far along the Sun was in its life cycle. If that failed to happen, the collapse would continue until a new form of pressure took over: electron degeneracy pressure, the quantum mechanical resistance to compression found in white dwarfs. But that's a story for another chapter. On the flip side, suppose the fusion rates suddenly spiked. Perhaps all the hydrogen atoms in the core decided to fuse at once, in an enthusiastic display of teamwork. The result would be a massive release of energy, increasing the pressure dramatically. The Sun would begin to swell, its outer layers puffing outward, cooling as they expanded. The star would become larger, redder and less dense, on its way to becoming a red giant. Again, nature does not allow this to happen unchecked. The system seeks balance, and any deviation from equilibrium triggers mechanisms to restore it, if it can. This balancing act does more than just hold the Sun together, it also determines its structure. The temperature, pressure and density at each layer of the Sun are set by the need to balance gravity and pressure. That's why the core is so hot and dense. It needs to generate enough energy to support all the layers above it. That's why the surface is so much cooler. It only needs to support the thin layers above it and radiate energy into space. And it's not just the Sun. Every star, regardless of its size, follows the same principle. Massive stars have stronger gravity, and therefore need much higher core temperatures and fusion rates to stay balanced. They burn through their fuel quickly and live short, brilliant lives. Smaller stars burn more slowly, their fusion rates lower, their lives longer, sometimes trillions of years. In all cases, hydrostatic equilibrium sets the pace and the path. Interestingly, this balance also affects the life cycles of stars. As a star exhausts its hydrogen fuel, it must find new sources of energy to maintain equilibrium. The core contracts, heats up, and begins fusing helium into heavier elements like carbon and oxygen. In more massive stars, this process continues, fusing progressively heavier elements until iron is reached. At that point, fusion stops being an energy-releasing process, and gravity takes over for good, leading to collapse and, depending on the mass of the star, either a supernova, a neutron star, or a black hole. But the Sun is not a massive star. It is, in cosmic terms, a gentle, middle-aged star, about halfway through its main sequence life. Its hydrostatic equilibrium is stable, its fusion reactions well-behaved, and its output remarkably constant. For us here on Earth, that constancy is a blessing beyond measure. It gives us seasons, daylight, weather and warmth. It allows ecosystems to evolve, civilizations to flourish, and people to plan picnics with some degree of confidence. The balance between gravity and pressure is not something we see or feel directly. It's not something we can touch or measure with a household thermometer. But it is the reason the Sun exists in its current form. It is the silent agreement between the forces of collapse and the forces of creation, a compromise between destruction and light. And perhaps that's the most beautiful part of all, that at the core of the Sun, where matter is torn apart and remade, where temperatures soar and particles collide with unimaginable force, there is peace, not stillness, but balance, a cosmic harmony sustained not by chance, but by the very laws of physics. It is this balance that has lit our skies for billions of years. It is this balance that will continue to shine for billions more. So the next time you look up at the Sun, casting shadows on the ground or setting the clouds ablaze in hues of gold and crimson, remember this: you're witnessing equilibrium. You're seeing the result of forces held in perfect tension, of chaos woven into order. You're watching a star that has found its centre, and in doing so has become a source of life, warmth, and wonder. The sun, ever burning, ever glowing, seems like a constant presence in the sky, a celestial companion that rises, sets, and repeats its path with the precision of a metronome. From our daily routines to the rhythms of the seasons, we live our lives under its steady influence. But in the grand scheme of cosmic time, the sun is not eternal. Like all stars, it has a lifespan, a beginning and an end, and it is currently in a rather comfortable middle-aged phase of life. This chapter of solar stability is known as the main sequence, and our sun is right in the heart of it. The concept of stellar lifespan is closely tied to the fuel that powers the star. In the case of the sun, that fuel is hydrogen, and it's being fused into helium in the core through the proton-proton chain, as we've gently explored in earlier chapters. This process releases energy, which in turn supports the sun against gravitational collapse and provides the light and heat we receive here on Earth. But hydrogen, abundant as it is not infinite. Even the sun's vast reservoir of hydrogen will eventually run out. To understand where the sun stands in its life cycle, it helps to know how stars are classified. The sun is a G-type main sequence star, also known more affectionately as a yellow dwarf. Despite the somewhat humble name, it is brighter than about 95% of the stars in our galaxy, many of which are smaller red dwarfs. The sun formed about 4.5 billion years ago and has been steadily fusing hydrogen ever since. It is expected to continue doing so for about another 4 to 5 billion years, giving it a total main sequence lifetime of roughly 10 billion years. So at the moment, the sun is like a healthy 40-something in star years. Not young, but far from retirement. It has settled into a long, stable period where the rate of hydrogen fusion balances the pull of gravity, creating the steady output of light and warmth we depend on. During this time, the sun's size, brightness, and temperature remain relatively constant, although it is slowly becoming more luminous over time. Yes, the sun is actually getting brighter. As fusion in the core proceeds, helium gradually builds up, and the core becomes denser. This causes the core to contract slightly and heat up, which increases the rate of fusion, and in turn the sun's overall brightness. It's a slow process. Over the past 4.5 billion years, the sun has grown about 30% brighter, and over the next few 100 million years, that trend will continue. This increase in luminosity has important implications for Earth. Even a small change in solar brightness can significantly affect the climate. In fact, in about 1 to 2 billion years, the sun's increased energy output will likely make Earth uninhabitable for complex life. The oceans may evaporate, the atmosphere could break down, and the surface temperature will rise to levels that no life as we know it could endure. It's not a sudden catastrophe, but a slow and steady shift, a gentle fade rather than a dramatic exit. But what happens after the main sequence ends? Once the sun runs out of hydrogen in its core, it will enter a new and very different phase of life. With no more hydrogen to fuse, the balance between gravity and pressure will tip. The core will begin to collapse under its own weight, and as it does, it will heat up. This increased temperature will eventually ignite the fusion of helium into heavier elements, like carbon and oxygen. At the same time, the outer layers of the sun will expand dramatically. The sun will swell into a red giant, a phase that will last for a few 100 million years. During this time, it will become hundreds of times larger than its current size, potentially engulfing the inner planets, including Mercury and Venus, and possibly even Earth. The surface of the red giant sun will be cooler, giving it a reddish hue, but the overall brightness will be much greater due to its sheer size. If you could stand on a distant moon like Europa or Titan during this time, assuming you had a good cooling system, you would see a truly enormous sun dominating the sky, glowing red and bloated, a stark contrast to the calm yellow disk we see today. Eventually, helium fusion in the core will also run out. The sun doesn't have enough mass to fuse carbon and oxygen into heavier elements, so it will shed its outer layers in a series of gentle but powerful pulses. These layers will drift off into space, forming a glowing shell of gas known as a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. They were simply named by early astronomers who thought they looked a bit like planetary disks through small telescopes. At the heart of this glowing nebula will remain the core of the Sun, now a white dwarf. This remnant will be roughly the size of Earth, but contain about half the Sun's original mass. It will no longer produce energy through fusion, but will shine faintly from the residual heat of its former self. Over trillions of years, it will gradually cool and dim, eventually becoming a cold, dark black dwarf, a hypothetical end state we've never observed, as the universe itself is not yet old enough for any white dwarfs to have reached this stage. This is the Sun's fate, to glow gently for billions more years, to swell into a majestic red giant, to cast off its outer layers in a luminous farewell, and to spend eternity as a quiet, cooling ember in the cosmic dark. And what does this mean for us? In the most immediate sense, nothing alarming. The Sun is stable and healthy. It has billions of years left on its main sequence clock, and any significant changes will happen far, far beyond the scope of human civilization. Our ancestors, 10,000 generations ago, saw the same Sun we see today, and if humanity continues to exist for another 10,000 generations, they too will see the same golden orb rising in the morning sky. But on a grander timescale, the Sun's lifespan is a reminder of how temporary even the most enduring things can be. We tend to think of stars as eternal, unchanging fixtures in the heavens, and yet they are born, they live, and they die. Their light is not permanent, it is borrowed, created through a dance of forces that cannot last forever. Still, there's a kind of poetic comfort in this cycle. The Sun will end, yes, but its death will not be in vain. The elements it produces during its life and death, helium, carbon, oxygen, will be scattered into space, enriching the interstellar medium, becoming the raw materials for new stars, new planets, and perhaps new life. In this way, the Sun story doesn't end. It continues, passed on like a flame to the next generation of stars, and we are part of that story. Every atom of carbon in your body, every molecule of oxygen in your lungs was once inside a star like the Sun. Not necessarily this Sun, but a star in an earlier generation, long gone and long silent, yet still speaking through the matter it left behind. So the Sun is not just our local heater, it is our heritage, our past and our future. A glowing reminder that in the cosmos everything is connected, and everything eventually changes. The Sun today shines with a steady light, but even that light carries within it the whispers of what's to come. Its gentle warmth is not the result of permanence, but of balance, and in time, that balance will shift. The story will move forward, and the Sun will take on new forms in its quiet journey through the ages. For now, though, we're in the golden years. The Sun, in its prime, shines down on a world full of life and wonder, and for billions of mornings yet to come, it will continue to rise, reliable and radiant, lighting the way for whatever future unfolds beneath its gaze. The Sun, as majestic and life-giving as it is not alone in its fusion work. Across the galaxy, stars of every size and temperament are busily fusing elements in their cores, turning hydrogen into helium, helium into carbon, and carbon into even heavier elements, all while releasing the energy that lights the universe. Our Sun may be a gentle and relatively mild-mannered star, but the cosmos is filled with overachievers, stars that are many times more massive, more volatile, and far more short-lived than our familiar yellow dwarf. These massive stars live fast and die young, burning through their nuclear fuel in the blink of a cosmic eye. But their lives, brief though they are, help forge the elements that make planets, people, and all the wonders of chemistry possible. While our Sun uses the proton-proton chain to carry out fusion, these larger stars often rely on a different fusion mechanism. the carbon-nitrogen-oxygen cycle, more commonly known as the CNO cycle. This reaction chain is more complex and requires higher core temperatures than the proton-proton chain, which is why it only dominates in stars more massive than the Sun. The CNO cycle still converts hydrogen into helium, just like the proton-proton chain, but it uses carbon, nitrogen and oxygen nuclei as catalysts, temporary holders that help the process along, but are ultimately regenerated by the end of the reaction. In this cycle, protons are fused onto carbon nuclei, transforming them step by step through various isotopes of nitrogen and oxygen, before returning back to carbon and releasing a helium nucleus in the process. It's a bit like borrowing your neighbour's ladder to paint your house. You use it for a while, move up and down with your paintbrush, and when you're done, you give the ladder back. The job is finished and the ladder is unchanged, ready to help someone else. In the same way, the carbon nucleus ends up exactly where it started, but along the way, it has helped fuse 4 hydrogen nuclei into one helium nucleus, releasing energy in the process. The CNO cycle is highly temperature sensitive. Its fusion rate increases dramatically with temperature, much more so than the proton-proton chain. This means that as a star's core heats up, the CNO cycle can quickly become the dominant fusion process. In massive stars, the core temperatures are often above 20 million degrees Celsius, making the CNO cycle an efficient and powerful engine. As massive stars burn through their hydrogen at a breakneck pace, they quickly progress to fusing heavier elements. Once hydrogen is depleted in the core, the star contracts under gravity, the temperature rises, and helium fusion begins. This is known as the triple alpha process, where 3 helium nuclei combine to form a carbon nucleus. From there, the fusion reactions build heavier and heavier elements. Carbon fuses into oxygen, oxygen into neon, neon into magnesium, and so on, creating a sort of elemental ladder inside the star. Each step up this ladder requires higher temperatures and pressures. The star becomes layered like an onion, with each shell fusing different elements. At the very centre is iron, the final stop on the fusion express. Iron, unlike the lighter elements, cannot release energy through fusion. It actually absorbs energy. So when a star's core becomes dominated by iron, fusion grinds to a halt. There is no more outward pressure to balance the force of gravity. In that moment, equilibrium collapses. The core can no longer support itself, and it collapses in a fraction of a second. The outer layers come crashing down, rebounding off the suddenly rigid core in a cataclysmic explosion, a supernova. These explosions are among the most energetic events in the universe. In just a few seconds, a supernova can release more energy than the Sun will emit over its entire 10 billion year lifetime. Supernovae do more than just dazzle the cosmos. They create the heavy elements that make up much of the periodic table. Gold, silver, uranium, and dozens of other elements are born in these brief, furious moments of stellar death. The iron in your blood, the calcium in your bones, the iodine in your thyroid, all of it was forged in the heart of a massive star or in the shockwave of a supernova long ago. We are, quite literally, made of stardust. Some supernovae leave behind exotic remnants. If the collapsing core has enough mass, it can become a neutron star, a city-sized ball of neutrons with the mass of the Sun. If it's even more massive, the core may collapse into a black hole, a region of space so dense and with gravity so strong that not even light can escape. These remnants are extreme, fascinating, and fundamentally different from anything our Sun will ever become. Our Sun, as we've gently explored, does not have the mass needed to go out with a bang. Its death will be a quieter affair, a slow puffing away of its outer layers, leaving behind a white dwarf. But in a way, the violence of other stars has already shaped our Sun's story. The cloud of gas and dust from which the Sun formed was enriched by earlier generations of stars that exploded, scattering the elements they made across the galaxy. Those elements gathered together again, coalescing into new stars and planets, into us. This idea, that every generation of stars builds upon the ashes of the last is one of the most humbling and beautiful truths in astronomy. The universe is not static. It is an ongoing act of creation and transformation. Each star, no matter its size or lifespan, plays a role in this grand recycling process. The light from those stars travels across vast distances, sometimes for billions of years, to reach us and tell their stories. Even in distant galaxies, we can observe stars of various types and ages. Some are just forming, their fusion engines only just beginning to ignite. Others are nearing the end of their lives, pulsing or swelling or dying in spectacular displays. And among them all, our sun shines as one unassuming participant in this grand cosmic ballet. A quiet star, but one with its own part to play. In comparing our sun to these more massive stars, we gain perspective. Our sun is neither the brightest nor the dimmest, neither the youngest nor the oldest. It is, in many ways, average. And yet, from that averageness comes extraordinary stability. Because of the sun's moderate mass, we enjoy billions of years of steady light and warmth, a luxury that many planets orbiting more massive stars may never have. Massive stars may be glamorous, they burn brighter, live faster, and die more dramatically. But they are also tempestuous. Their intense radiation can strip atmospheres from nearby planets. Their short lives give little time for complex life to emerge. In contrast, the sun's slow and measured pace has nurtured Earth through eons of change, giving life time not just to survive, but to flourish. So while it's fascinating to marvel at the fireworks of supernovae and the exotic remnants they leave behind, there's something equally awe-inspiring about the quiet consistency of our own star. It reminds us that there is strength in stability, power in patience, and beauty in the seemingly ordinary. And still, the story continues. Across the galaxy, stars are forming, fusing, and fading. Each one contributes to the vast web of creation that spans the cosmos. Our sun is part of that web, one node in an intricate tapestry of energy and matter, life and light. As we look up at the night sky and see the stars twinkling from across the gulfs of space, we're not just seeing distant points of light. We are seeing the past. We are seeing chemistry in action. We are seeing the engines of fusion at work, shaping the universe one element at a time. And in that quiet, twinkling brilliance, there is a message that everything is connected, that every atom has a history, and that somewhere, in the heart of a distant star, the seeds of future worlds are already being formed. So the next time you look at the sun, let it remind you not just of its own quiet fire, but of the great stellar family it belongs to. A family of fusion, of light, of creation. A family of stars, some still shining, some long gone, but all part of the same incredible story. Every morning, when the sun rises above the horizon and casts its golden light across the landscape, it's easy to take it for granted. The warmth on your face, the glow that illuminates the sky, the subtle shift of shadows, all feel so familiar, so automatic. But behind this daily miracle lies a vast and intricate truth. Nearly everything we see, everything we eat, everything we breathe, and everything we are depends, in one way or another, on nuclear fusion happening 93 million miles away, in the heart of the sun. Solar fusion is not just a scientific curiosity, it is the foundation of life on Earth. From the tallest trees to the smallest microbes, from ocean currents to weather patterns, from ancient civilizations to the glow of a campfire, everything is woven together by the quiet, steady pulse of the sun. Let's begin with something green, plants. Without the sun, they could not exist. Plants use sunlight to carry out photosynthesis, a process that converts carbon dioxide and water into glucose and oxygen. This is not just a side project. It's the primary method by which energy from the sun is captured and stored in living systems. The glucose provides energy and building blocks for the plant's growth, while the oxygen is released into the atmosphere, giving us the air we breathe. When you look at a tree, you're seeing sunlight stored in wood. When you bite into an apple, you're tasting sunshine transformed into sugar. Even the scent of freshly cut grass or blooming flowers is, in some quiet way, an echo of the sun's light. Through photosynthesis, solar energy enters the food web. Herbivores eat the plants, carnivores eat the herbivores, and everything eventually circles back to the sun. But the influence of the sun goes even deeper. Long before humans ever walked the earth, ancient plants and microorganisms captured solar energy in their tissues. Over millions of years, as they died and were buried under sediment, their remains transformed into coal, oil, and natural gas. These fossil fuels are quite literally the stored energy of ancient sunlight. When we burn them to heat our homes or power our cars, we are releasing energy that was first captured hundreds of millions of years ago. It's a curious thought. The gas in your car, the coal in a power plant, the electricity in a light bulb, all trace their lineage back to photons born in the sun's core, released through fusion reactions so long ago that dinosaurs still roam the earth when the light finally reached the surface. Even our bodies are sustained by sunlight. The carbohydrates, fats, and proteins we consume all originated from photosynthetic organisms. Every cell in your body runs on energy derived from food, which in turn came from plants or animals that ate plants, and those plants of course relied on the sun. There's a poetic irony in the fact that we spend our lives under the sun, using its light to see and move and grow, all while being powered by the energy it gave us long before. In a way, we are walking solar batteries, moving, thinking, dreaming collections of sunlight turned into flesh. But fusion's influence isn't limited to biology. The sun also drives the climate and weather. When solar radiation strikes Earth, it heats the surface unevenly. Equatorial regions receive more direct sunlight, while the poles receive it at a slant. This uneven heating sets the atmosphere in motion. Warm air rises at the equator and moves toward the poles, while cooler air sinks and moves toward the equator. These movements create wind patterns, ocean currents, and the complex dance of clouds, storms, and seasons. The sun also powers the water cycle. It causes water to evaporate from oceans, lakes, and rivers. That vapor rises, forms clouds, and eventually returns as rain or snow. This cycle shapes the landscape, nourishes crops, fills reservoirs, and quenches thirst. It's easy to forget that even the gentle patter of raindrops on your window is a gift from fusion. Indirect, yes, but essential. Our cultural and psychological lives are shaped by the sun as well. Humans have worshipped the sun for millennia, building temples to its rising, tracking its movements, and celebrating its return at the solstice. The sun has been a symbol of life, power, clarity, and rebirth in nearly every civilization. We measure our days by its rising and setting. We schedule our activities around its presence in the sky. Even our mood is influenced by its light. Seasonal affective disorder, for example, is a reminder of how much we need sunshine, not just to see, but to feel whole. And then there's time. The Earth's orbit around the sun defines the year. The tilt of our axis relative to the sun gives us seasons. The rotation of the Earth, facing toward and away from the sun, gives us day and night. Our calendars, our holidays, our sense of morning and evening, all are based on our relationship with a star burning in the sky. Light from the sun has also shaped our technology. Solar panels capture photons and convert them directly into electricity. As the world moves toward more sustainable energy sources, we are increasingly turning back to the sun, looking for ways to harness its power more efficiently. Solar farms now dot landscapes across the globe, quietly converting sunlight into energy. In space, satellites rely on solar panels to keep their systems running, drawing power from the same light that filters through your bedroom curtains. The sun has even helped us understand our place in the universe. The study of sunlight, its spectrum, its variations, its interactions with Earth, has led to countless scientific discoveries. By observing how sunlight is absorbed or reflected, we've learned about the composition of our atmosphere, the ozone layer, and the greenhouse effect. Sunlight helps us monitor climate change, track weather patterns, and study other planets. And speaking of other planets, without the sun, there would be no planets at all. Our solar system formed from a swirling disk of gas and dust, collapsed under gravity. At the centre, the sun ignited. Around it, the remaining material coalesced into planets, moons, asteroids, and comets. The heat and light from the sun shaped their surfaces, their climates, and their chemistry. Mars once had rivers. Venus has a runaway greenhouse effect. Earth, balanced just right, found itself in the habitable zone, the narrow region where liquid water can exist, and where life as we know it could begin. It's remarkable, really, how many different threads of existence tie back to that one process: nuclear fusion, a reaction that happens quietly, constantly, in the sun's core. A process that doesn't roar or crackle, but releases energy gently, steadily, and reliably. And that energy spreads outward, through the layers of the sun, across the vacuum of space, through the sky, into our world, and into us. It is fusion that lights the morning dew and powers the hum of bees. Fusion that drives the winds and carves the coastlines. Fusion that warms your coffee, your home, your skin. Fusion that gave rise to the forests, the fields, the oceans, and the cities. Fusion that made possible the first breath of a newborn and the final sigh of an ancient tree. So the next time you step into the sunlight, pause for just a moment. Feel its warmth. Close your eyes. That heat began in a place you will never see, in the heart of a star, in the delicate dance of particles, in the quiet conversion of matter into energy. That light is not just brightness, it is nourishment, it is movement, it is life. You are, in the most literal sense, solar-powered. You're a symphony of atoms once forged in stars and now fueled by their light. Every heartbeat, every thought, every smile is made possible by a fusion reaction that began over 4 billion years ago and continues to this day, quietly, faithfully, brilliantly. The sun does not shine for us, of course. It shines because it must, because physics says it will, until the day its fuel is spent. But in that shining, in that relentless giving of light, we find our meaning. We are the children of fusion, and we carry its fire in everything we do. For as long as we have looked up at the sun, humans have dreamed of harnessing its immense power here on Earth. The idea is as simple as it is ambitious: to replicate the very process that powers the stars, nuclear fusion, and use it to generate clean, nearly limitless energy. No carbon emissions, no dangerous long-lived radioactive waste, no dependency on fossil fuels, just pure radiant power drawn from the most abundant elements in the universe. It almost sounds too good to be true, and in some ways, for now, it still is. But the dream of fusion energy isn't a fantasy. It's a work in progress, an engineering and scientific challenge of breathtaking scale. The same forces that allow fusion to occur effortlessly in the heart of the sun become extraordinarily difficult to reproduce in the controlled environments of human technology. But the rewards are so profound that scientists and engineers across the globe have spent decades, many lifetimes, pushing the boundaries of what's possible. To understand the challenge of fusion on Earth, let's first recall what makes it work so beautifully in the sun. At the core of our star, gravity provides both the pressure and the confinement necessary to bring hydrogen nuclei close enough together for the strong nuclear force to bind them. The temperature is around 15 million degrees Celsius, and the density is more than 150 times that of water. These extreme conditions allow protons to overcome their natural repulsion and fuse, releasing energy. Here on Earth, we don't have the luxury of solar mass and gravity. If we want fusion, we have to create those conditions ourselves. That means finding ways to heat hydrogen isotopes, typically deuterium and tritium, to temperatures of over 100 million degrees Celsius, which is hotter than the core of the sun. At those temperatures, the fuel becomes plasma, a state of matter in which electrons are stripped from atoms, creating a charged, energetic soup of nuclei and free electrons. But heat alone is not enough. We must also confine the plasma long enough for the nuclei to collide and fuse, and we must contain it without it touching anything solid, because no known material can survive such temperatures. It's like trying to hold a piece of the sun in a cage made of magnets. This is where fusion research becomes a symphony of precision and innovation. There are two primary approaches to fusion energy: magnetic confinement and inertial confinement. Each has its own set of challenges, technologies, and fascinating quirks. Let's begin with magnetic confinement, which is the more mature of the two. The most well-known design in this category is the tokamak, a donut-shaped device that uses powerful magnetic fields to confine plasma in a circular loop. Inside a tokamak, deuterium and tritium are injected and heated until they become plasma. Superconducting magnets then create a magnetic field that holds the plasma in place, preventing it from touching the walls. The goal is to maintain this plasma at high enough temperature and pressure for long enough that fusion reactions begin to occur in meaningful numbers. When deuterium and tritium fuse, they form a helium nucleus and a high-energy neutron. The neutron escapes the magnetic field and can be captured by a surrounding blanket of material, transferring its energy and generating heat. That heat can then be used to produce steam and drive turbines, just like in a conventional power plant. Tokamaks have been around since the 1950s and have steadily advanced in complexity and performance. The largest and most ambitious project to date is ITER, the International Thermonuclear Experimental Reactor, currently under construction in southern France. A collaboration between 35 countries, ITER is designed to be the first fusion device to produce more energy than it consumes, a milestone known as ignition or net energy gain. Once complete, ITER will be the size of a small building, with magnets weighing hundreds of tons and a plasma volume of over 800 cubic meters. It will use deuterium and tritium fuel heated by a combination of microwave and particle beam systems. The goal is to produce 500 megawatts of fusion power from 50 megawatts of input energy, a tenfold return. If ITER succeeds, it won't generate electricity directly, but it will prove the viability of fusion as an energy source. Future plants, based on its design, could follow in the decades to come. ITER's motto, fittingly, is bringing the sun to Earth. Then there is inertial confinement, an entirely different approach that seeks to compress a small pellet of fusion fuel using intense bursts of energy. This is typically done with lasers, enormous, precisely calibrated lasers that deliver a symmetrical pulse of energy to the outside of the fuel pellet. The outer layer of the pellet rapidly explodes outward, and by Newton's third law, the inner core is compressed inward to extreme densities and temperatures. The most advanced example of this approach is the National Ignition Facility, or NIF, located in California. It uses 192 laser beams to deliver energy to a target the size of a peppercorn. In December 2022, NIF made headlines by achieving a small but historic milestone, a fusion experiment that produced more energy than the laser energy used to initiate it. Though the overall system still consumed far more energy than it produced, this was a clear sign that the physics of fusion work as expected. Inertial confinement holds promise for certain applications, including potential future energy production and military research. But the engineering challenges remain steep, especially when it comes to repeating the process quickly, efficiently, and reliably. Beyond tokamaks and lasers, there are other fusion concepts being explored. Stellarators, for example, are similar to tokamaks but with twisted, more complex magnetic fields that can provide continuous operation without the need for a central current. Field reverse configurations, magnetized target fusion, and even fusion-fission hybrid reactors are all under investigation. Private companies have also entered the race, bringing a spirit of startup innovation to a field long dominated by government laboratories. Companies like Commonwealth Fusion Systems, TAE Technologies and Helion Energy are developing compact high-field fusion devices using advanced materials and cutting-edge computing to accelerate progress. Some aim to deliver functional fusion power plants within the next decade. An ambitious goal, to say the least, but one that reflects growing optimism and investment. Despite the complexity, the motivation is clear. Fusion promises enormous advantages. Its fuel sources, deuterium from water and tritium bred from lithium, are abundant. A single litre of seawater contains enough deuterium to power a household for hundreds of years in theory. Fusion does not produce greenhouse gases, and unlike fission, it does not generate long-lived radioactive waste. There's no risk of a runaway reaction or meltdown, and the byproducts are mostly helium, a harmless, inert gas. But fusion is not easy. Achieving ignition is a feat. Sustaining it is even harder. Making it practical, economical, and scalable is the final mountain to climb. Yet progress is steady, and each milestone brings us closer to a future powered not by burning fuel, but by replicating the stars. There is something poetic about the idea that humanity might one day light its cities, power its industries, and charge its devices using the same process that makes the sun shine. Fusion is more than just a technology. It's a connection to the cosmos, a reminder that the laws of nature are not obstacles but invitations. They challenge us, yes, but they also guide us. The journey from starfire to power plant is one of the most extraordinary quests in science. It is a testament to human curiosity, perseverance, and imagination. To replicate the sun's furnace in a magnetic cage, to coax atoms into merging, to bottle the energy of the universe's birthplaces, that is no small dream. But it is one we continue to chase. And when we finally succeed, when a fusion power plant hums quietly, lighting homes and warming hearts without pollution or peril, we will have done more than just solve an engineering problem. We will have forged a new relationship with the universe, one where we no longer burn the past but borrow from the stars. So the next time you feel the warmth of the sun or see its golden light stretch across the floor, remember, this is the power we seek, not to dominate, but to understand, to emulate, and to share. Fusion may be the oldest light in the universe, but for us, it may also be the key to a brighter, cleaner, and more sustainable future. As steady and familiar as the sun seems to us, rising each morning, setting each evening, it remains full of mystery. For all that we've learned about fusion, light, and solar structure, there are still puzzles hidden within its blazing face and beneath its turbulent skin. The sun, it turns out, is far from being a calm and predictable sphere of gas. It seethes with magnetic fields, flares with sudden outbursts of energy, and spins with cycles that ebb and flow in ways we're only beginning to understand. And at the heart of some of the greatest solar mysteries lies a counterintuitive truth. The sun's outermost layer, the corona, is somehow hotter than the layers below it. That might sound like a mistake. After all, we expect things to get cooler as we move away from a heat source. Imagine sitting near a campfire. The closer you are, the warmer you feel. Move away, and the temperature drops. But the sun, as usual, doesn't behave like a campfire. Its core burns at around 15 million degrees Celsius. As you move outward into the radiative and convective zones, the temperature gradually decreases, dropping to around 5,500 degrees at the photosphere, the visible surface of the sun. And then something very strange happens. Instead of continuing to cool, the temperature begins to climb again. By the time you reach the corona, the sun's outer atmosphere, it can soar to over 1 million degrees Celsius, and in some regions, it may even reach 10 million degrees. This phenomenon is known as the coronal heating problem, and it's one of the longest-standing and most intriguing questions in solar physics. How can a layer that is further from the core be so much hotter than the layers beneath it? What mechanisms could be at play, pouring energy into the sun's outer atmosphere and heating it to such extreme temperatures? One promising explanation involves the sun's magnetic field. The Sun is a magnetically active star with field lines that twist, tangle, and snap in complex patterns. These magnetic fields emerge from the solar interior and arc through the corona in great looping structures. When these loops become unstable, they can release energy in bursts known as magnetic reconnection. During reconnection, oppositely directed magnetic field lines break and rejoin, converting magnetic energy into heat and kinetic energy. This process is thought to be a key player in heating the corona. You can picture it like stretching a rubber band until it snaps and releases a small burst of energy. Now imagine millions of magnetic rubber bands twisting and snapping all over the Sun's surface every second. The cumulative energy of these events could account for the million-degree temperatures observed in the corona. Another possible explanation involves waves, specifically Alfvén waves, a type of magneto-hydrodynamic wave that travels along magnetic field lines in a plasma. These waves can be generated by the turbulent motions of the convective zone and may propagate upward into the corona. If they dissipate their energy at the right locations and in the right ways, they could contribute significantly to coronal heating. However, this process depends on a delicate balance. The waves must not only carry enough energy, but also transfer it to the coronal plasma efficiently. Whether this occurs is still an open question. The truth may involve both processes, and perhaps others we haven't yet discovered. What's clear is that the corona behaves in ways that defy intuition, and that understanding it requires untangling the Sun's complex magnetic ballet. The Sun's magnetic activity doesn't stop at heating the corona. It also manifests in dramatic and sometimes violent outbursts, such as solar flares and coronal mass ejections. A solar flare is a sudden, intense burst of radiation caused by the release of magnetic energy stored in the Sun's atmosphere. These flares can release as much energy as 1 billion megatons of TNT in just minutes. They emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, and can affect Earth's ionosphere, disrupting radio communications and GPS signals. Coronal mass ejections, or CMES, are even more powerful. These are massive bubbles of plasma and magnetic field that erupt from the Sun and can travel through space at speeds of over 2 million kilometers per hour. If a CME collides with Earth's magnetic field, it can cause geomagnetic storms, potentially damaging satellites, power grids, and communication systems. The most intense storms can even generate brilliant auroras, painting the sky with green and red light far from the poles. One of the most famous geomagnetic storms in recorded history occurred in 1859. Known as the Carrington event, it caused telegraph systems across Europe and North America to fail, sometimes shocking operators and sparking fires. If an event of that magnitude were to happen today, the impact on our modern, electronics-dependent world would be profound. Because of this, scientists closely monitor solar activity, looking for signs of flares and CMEs. Satellites like NASA's Solar Dynamics Observatory and the European Space Agency's Solar and Heliospheric Observatory, SOHO, keep constant watch on the Sun's surface and atmosphere. They help us understand the dynamics of solar storms and improve our ability to predict when and where their effects might be felt on Earth. But even with these tools, predicting solar activity remains a challenge. The Sun follows an 11-year cycle of magnetic activity, known as the solar cycle. During solar maximum, sunspots, flares, and CMEs are more common. During solar minimum, the Sun's surface appears calmer. These cycles are linked to changes in the Sun's magnetic field, which flips polarity approximately every 11 years. But the precise mechanisms driving the cycle and its variations from one cycle to the next are still not fully understood. Sometimes the cycle is unusually quiet, such as the Maunder minimum, which occurred between 1645 and 1715. During this period, very few sunspots were observed, and the northern hemisphere experienced significantly colder winters. Some scientists suspect a connection between low solar activity and climate patterns, though the relationship is complex and still debated. At the other end of the spectrum, we sometimes see particularly active cycles with higher numbers of sunspots and solar storms. These variations remind us that the sun is not a static, unchanging light bulb in the sky. It's a dynamic, living system, constantly evolving and surprising us. Then there's the question of internal flows and the solar dynamo, the process believed to generate the sun's magnetic field. Deep within the convective zone, plasma moves in complex patterns, creating currents and turbulence. As the sun rotates, these flows twist and shear the magnetic field lines, amplifying them and creating large-scale magnetic structures. But modelling this dynamo process is difficult. The equations governing plasma and magnetism are non-linear and highly sensitive to initial conditions. Even the most powerful supercomputers struggle to simulate the full complexity of the solar interior. Adding to the mystery is the phenomenon of differential rotation. The sun does not rotate like a solid body. Its equator rotates once approximately every 25 days, while the poles take about 35 days to complete a rotation. This difference in rotation speed stretches and twists the magnetic field, contributing to the buildup of magnetic energy and the eventual release in flares and CMEs. The interface between the radiative zone and the convective zone, a region called the tachocline, is thought to play a key role in the solar dynamo. It's a thin, shearing layer where rotational speed changes abruptly. But since we can't directly observe the solar interior, we rely on helioseismology to infer its properties. This field studies the oscillations and sound waves travelling through the sun, using them to probe its internal structure. Much like seismologists use earthquakes to study the Earth's interior, there is so much we still don't know. Why do some solar cycles last longer than others? What determines the strength of a given cycle? Could we one day predict solar max and minima with the same confidence we forecast the weather? Might there be long-term cycles hidden beneath the 11-year rhythm that affect the sun over centuries or millennia? The sun keeps its secrets well, wrapped in plasma and hidden behind a veil of blinding light. But with each passing year, our instruments grow sharper, our models more refined, and our understanding deeper. From the puzzle of the hot corona to the riddle of the magnetic cycle, the sun invites us to keep asking questions, to keep looking up, and to keep searching for answers in the light. And maybe, just maybe, that's part of the sun's role, not only to warm the earth and sustain life, but to inspire curiosity, to be, in its brilliance and its mystery, a constant reminder that the universe is vast, that there is always more to learn, and that wonder never sleeps. For a star that has burned for more than 4 billion years, the sun is surprisingly elusive. Its searing brightness prevents us from looking directly at it, and its very nature, a churning ball of plasma without a solid surface, defies direct exploration. And yet, through ingenuity, patience, and an array of clever instruments, scientists have found ways to study the sun in remarkable detail. From ground-based observatories to spaceborne satellites, from neutrino detectors buried deep underground to probes skimming the edge of the solar corona, we are learning more and more about our star with each passing year. Watching the sun is not as straightforward as watching a bird or a passing cloud. You can't simply point a telescope at it during your lunch break. The sun's brilliance is so intense that it can damage eyes and instruments alike. Specialized filters, cameras and techniques are needed to peer into its different layers, from the visible photosphere to the dynamic corona, and to measure its magnetic fields, oscillations, particle emissions, and light at every possible wavelength. Let us begin with perhaps the most iconic of all solar observatories, SOHO, the Solar and Heliospheric Observatory. Launched in 1995 as a joint mission between NASA and the European Space Agency, SOHO was designed to study the sun from its deep core to its outer atmosphere. Positioned at the first Lagrange point, about 1.5 million kilometers from Earth, it has a constant view of the sun, unobstructed by Earth's rotational weather. SOHO carries a suite of instruments that allow it to observe the sun's internal vibrations, track sunspots, study solar wind, and monitor solar storms. One of its key achievements has been in the field of helioseismology, the study of waves travelling through the sun's interior. Much like seismologists use earthquakes to map the structure of the Earth, solar physicists use these oscillations to infer details about the sun's hidden interior, including the behaviour of plasma flows and the rotation of different layers. SOHO has also become an accidental comet hunter. Its cameras, designed to watch for coronal mass ejections and solar flares, have detected thousands of comets passing near the sun, many of them plunging to their fiery demise. These discoveries have added an unexpected chapter to the mission's legacy. More recently, NASA's Solar Dynamics Observatory, or SDO, has taken solar observation to new heights. Launched in 2010, SDO provides ultra-high-definition images of the sun, capturing details on scales as small as 100 kilometers. It observes the sun in multiple wavelengths of extreme ultraviolet light, revealing the complex dance of plasma and magnetic fields in the chromosphere and corona. SDO produces an astonishing amount of data, over a terabyte every day, and its images are not just scientifically valuable, but visually stunning. Time-lapse videos created from SDO's data show the sun as a living, breathing entity. Loops of plasma arc over the surface, flares burst outward, sunspots rotate into view, and the entire disk pulsates like a drum. But sometimes, even high-resolution images from a distance aren't enough. Enter the Parker Solar Probe, a mission so bold it almost sounds like science fiction. Launched in 2018, the Parker Solar Probe is on a mission to touch the sun, or at least get as close to it as humanly or robotically possible. Over the course of 7 years, the probe will complete 24 orbits, each one bringing it closer to the solar surface. Its closest approach will take it within just over 6 million kilometers of the sun's surface, roughly 7 times closer than any spacecraft has ever been. At that distance, the sun's heat and radiation are intense beyond imagination, yet Parker is equipped with a revolutionary heat shield made of carbon composite material that keeps its instruments at room temperature, while the exterior bakes at more than 1,000 degrees Celsius. The Parker Solar Probe is providing groundbreaking data on the solar wind, the stream of charged particles flowing from the sun into space, and on the structure of the solar corona. It's already helped answer long-standing questions like why the solar wind accelerates so dramatically as it leaves the corona, and why the sun's magnetic field seems to flip and twist in sudden, unexpected ways. Then there's the European Space Agency's Solar Orbiter, launched in 2020. While Parker flies in close, Solar Orbiter maintains a more distant orbit, allowing it to observe the sun's poles, regions that are difficult to see from Earth. Understanding the polar magnetic fields is key to unraveling the mysteries of the solar cycle and predicting solar activity. Together, these missions form a kind of cosmic observatory, each contributing a different perspective. They help us understand not only what the sun is doing now, but how it has changed over time and how it might behave in the future. Of course, not all observations happen in space. Earth-based solar telescopes also play a critical role. The Daniel K. Inouye Solar Telescope in Hawaii is currently the world's most powerful ground-based solar observatory. Its 4-meter mirror allows it to resolve features on the sun as small as 30 kilometers across, revealing sunspot structures, convection cells, and magnetic fields with unprecedented clarity. But the sun is not only watched with telescopes, it is also listened to in a way. Helioseismology uses tiny vibrations on the sun's surface to study the interior, vibrations caused by sound waves bouncing through the sun's plasma. These waves are measured in oscillation patterns on the photosphere, the visible surface of the sun. By analysing these patterns, scientists can infer details about the temperature, density, and motion inside the sun. Other observations happen deep underground. Neutrino detectors such as the Super Kamiokande in Japan or the Sudbury Neutrino Observatory in Canada monitor the ghostly particles produced in the Sun's core. These detectors are located beneath kilometers of rock to shield them from cosmic rays and other background noise. When a neutrino interacts with a molecule of water or heavy water, it produces a tiny flash of light, captured by sensitive instruments. These detections allow scientists to monitor fusion directly and in real time. By studying neutrinos, we can confirm that the Sun is still fusing hydrogen into helium in its core. Right now, not just millions of years ago, when the photons of sunlight began their journey outward. Neutrinos provide a kind of instant solar report, while light gives us a historical record. All of this data, from light, from particles, from waves, converges into our growing understanding of the Sun. With every solar flare, every sunspot, every neutrino detected, we refine our models and predictions. We learn not only how the Sun behaves, but how its behavior affects Earth. Solar observation has practical implications as well as scientific ones. By monitoring solar activity, we can better predict geomagnetic storms and protect satellites, communication networks, and power grids. We can anticipate disruptions to GPS systems, airline communication, and even astronaut safety aboard the International Space Station. And as we prepare to venture farther into space, returning to the Moon, reaching for Mars and beyond, the need to understand solar radiation becomes even more urgent. The Sun is our greatest ally, but it can also be a formidable challenge for space travel. Predicting its moods could one day be as vital as checking the weather before a sea voyage. But perhaps what's most remarkable about our solar observations is the perspective they offer. The Sun, once seen as a deity or a mysterious disk in the sky, is now a subject of daily scrutiny and deep scientific insight. We watch its every flicker, measure its every wave, and model its every heartbeat. We have sent machines into its atmosphere, unraveled the secrets of its light, and traced the journey of particles born in its core. Yet, for all we've achieved, the Sun still holds its secrets. New discoveries await in the twist of a magnetic loop, the pulse of a sunquake, or the whisper of a neutrino. Every observation leads to new questions, and every answer shines light on another mystery. In the end, to watch the Sun is not just to study a star, it is to witness a force that has shaped our world in every conceivable way. It is to glimpse the engine of life, the origin of time, the beacon of our solar system, and as we continue to watch, with instruments more precise and questions more refined, we do more than just observe. We participate in the long, quiet dialogue between humanity and the cosmos, a dialogue that began with shadows and sundials and now unfolds in the language of photons, plasma, and magnetic fields. The Sun is not merely seen, it is known, and it is still being discovered. And so, after this long and winding journey through light and heat, gravity and plasma, particles and waves, we find ourselves returning, ever so gently, to the quiet wonder we began with. The Sun, that ever-burning star, remains above us still. Not just a glowing disk in the sky, but a living engine of fusion, a celestial clock, a maker of weather, and the spark of all that breathes. We've traced its life from its birth in a cloud of dust to its current golden middle age. We've unraveled the intricate process of nuclear fusion, explored how this fiery heart shapes our world, and dreamed of capturing its power here on Earth. We've delved into the secrets of solar storms, puzzling temperatures and magnetic mysteries, all while gazing through telescopes, listening to neutrinos, and sending brave little spacecraft ever closer to the blaze. And through it all, one thing has remained constant: our quiet fascination with the star that never sleeps. Because the Sun never rests, not for a second. Its light may help us drift off to sleep each evening, but it is forever awake, burning, churning, humming softly through the silence of space. Perhaps as you rest now, you find yourself thinking back to those gentle questions we began with. Where are you right now, watching or listening? What time is it in your little corner of the world? Is it morning, with golden rays creeping across the windowsill, or night, with the sky dark and the sun tucked away beneath your feet, still shining on the other side. And perhaps now you wonder, after everything you've heard, did the story soothe you? Did it spark a little curiosity, or maybe even too much to fall asleep right away? If so, I do hope it was worth it. Because drifting off with wonder in your heart is a fine way to end the day. If you've enjoyed this quiet exploration under the wing of our sleeping sun, do consider giving it a like or subscribing to the channel. It helps keep the light on, so to speak, and it lets me know you'd like more stories like this to accompany your evenings. Wherever you are and whatever the hour, I wish you peace, rest, and just enough curiosity to carry into your dreams. And of course, always remember, this is for relaxation and wonder, not medical advice. Sleep well and let the sun keep watch.